All right, any other questions? Okay, yeah, let's talk a little bit about boundary conditions. So last time we only talked about one particular boundary condition, that is u at L equal to u at right equal to 0, right? Oh, actually no, we actually talk about ul and u right equal to a particular value, right? So let's say are fixed. Okay, so today let's talk about two different types of boundary conditions. So these are called Dirichlet boundary conditions. BC means boundary conditions. So that means the value of the solution at the boundary is fixed. And another type is the derivative at the boundary is fixed, is equal to a set value, let's say A. So these are called Neumann boundary conditions. Okay, think of, in the case of a heat equation that models the heat transfer, the temperature distribution over a one-dimensional bar or spring. So if you have a Dirichlet boundary condition, what does that mean if the solution is the temperature?
Heat sink of source.
Yeah, that means a heat sink of source that has a certain temperature set. So let's say a big piece of metal whose temperature is basically constant. All right. Now, what if I have a Neumann boundary condition? What does that correspond to? That means a set heat flux. For example, a particular type of Neumann boundary condition is that I insulate over one side of the domain. So there is no heat flux. No heat flux means there is no temperature gradient. That means the temperature gradient is equal to 0. That corresponds to the case that A equal to 0. Right? Another case is when I have a heat source that outputs a particular watt, a particular heating, like rate of heating on one side. Then I also know the temperature gradient because I know what is the amount of heat being conducted per unit time. So this is where Neumann boundary conditions are useful. So if I have a Neumann boundary condition, let's say what is my matrix A. So A is an approximation to the first order derivative. So let's look at a particular equation, right? Let's look at a particular equation. Let's look at the second derivative of u equal to f. That being discretized into A u equal to f. So let's say I apply one side, the left-hand side being Neumann boundary condition, the right-hand side being Dirichlet boundary condition with 0 to make it simple. Now, what is my matrix A that represent this differential operator and this boundary condition? So first of all, starting from the second line, it is exactly the same as what we had last time. Starting from the second row, we still have 1 over delta x squared minus 2 over delta x squared, 1 over delta x squared, and etc. It's a tridiagonal matrix up to the very last line because I have the Dirichlet boundary condition at the right hand side, so that doesn't change anything starting from the second row. Can somebody tell me what is the first row?
1 minus
1 minus 1. Why is that?
we want to keep the flux same between the boundary point and the first point.
We want to have the difference between the first point and the second point. That is because that's a very good very good answer. The reason for this is that we want the first line to be a discretization of this boundary condition. And the discretization of the boundary condition is the following: is u at the second grid point minus u at the first grid point divided by delta x is equal to a.
Minus 1 and
Right, so if I put 1 and minus 1, what is going to be my right hand side?
minus a over delta x.
Yes, so my right hand side from the second line on is the same, it's f2, etc., etc. But the first one thus has nothing to do with f. The first line, if you put 1 and minus 1 here, that is going to be minus a over delta x. Okay. Or I usually like making the magnitude of each line to be similar to the rest of these entries, because I mean, if you studied linear algebra and know what is called a condition number, you probably know it's a good idea to have like all the entries in the matrix to be roughly the same magnitude. So if I write, yeah, and I usually put the minus sign here so that like the signs are consistent. So if you have minus 1 over delta x squared and 1 over delta x squared, what you have is a over delta x, exactly. So that's a good discretization of the boundary condition. And of course, it is only if this is a first order discretization. Because if you do Taylor series analysis, you're going to find out the truncation area at that point is proportional to delta x. If you want higher order discretization, you know what to do, right? If you don't look over the lecture on Friday, so you know how to construct arbitrary order of accuracy schemes using either centered or biased stencil. By the way, a stencil means like what are the points you get involved in constructing the finite difference operator. All right, any questions on this? And if you are curious, it's interesting to think of another type of boundary condition that is called a mixed boundary condition. So that's the partial derivative plus a mu times u plus a constant. Basically, it's a linear combination of derivative and value equal to something, equal to a given number. So you can figure out, if I have something like this, what the matrix is going to be. All right. Okay, good. So let's, if you don't have any questions, we are going to move to 2D. Questions? No?